Matthews Gatos here. In this video, we're going to look at how to apply the power rule. So let's get started. In our last video, we looked at given f of x is equal to x to the exponent of n, so any power at all, we can find the derivative by bringing that exponent down and raising it to 1 less than the original exponent. So what I'm going to do now is use a whole bunch of examples applying this power rule. Okay, so here we go. Let's find the derivative of the following functions. F of x is equal to x exponent 7. So to find the derivative, I bring the 7 down and multiply it by the power with 1 less exponent. So bring the 7 down, reduce the 7 by 1. So much easier than the limit definition. Okay, let's look at this one. F of x is equal to 1 over x exponent 4. So it doesn't look like a power right now. So my tip is to write it as a power using your laws of exponents. So 1 over x exponent 4 is the same as x to the negative 4. So now that it's a power, let's apply the power rule. So bring the negative 4 down and decrease your exponent by 1. So negative 4 decreased by 1 is negative 5. Now we can't leave our answer with negative exponents, so I just need to write it as negative 4 multiplied by x exponent, positive 5 in the denominator. Let's try another one. So in this one here, square root of x. So again, I want to write that as a power so that I can apply the power. So I'm going to write that as x to the exponent of 1/2. So to do the derivative, I bring the exponent down and decrease my power by 1. So 1/2 take away 1 is negative 1/2. So I want to write this with a positive exponent. So it's 1 divided by 2, and then I'm going to bring the x to the negative 1/2 down. And because I started with roots, I'm going to end with roots. So I'm going to write that as 1 over 2 root x. Okay, one more. We're going to again write this as a power. So using our laws of exponents and switching from exponential to radical form, I know I can write this as x to the exponent of 2 over 3, raising it to the power of 2, taking the third root. So the derivative is bring the exponent down 2/3, decrease your exponent by 1. So 2 over 3 take away 1 is negative 1 over 3. So let's write that as, so here's my fraction 2 over 3. To make the exponent negative, I bring it to the bottom and now it's positive exponent. But I started with roots, not exponents, so I want to end with roots. So this is 2 over 3 times the cube root of 3. And I'm just going to use brackets so you can see that it's the cube root, not the 33rd root. Okay. So those last examples all had a coefficient of 1 in front. So I want to look at what happens when I have something, not just f of x, I have a constant in front. So if g of x is equal to c times f of x, then g prime of x is equal to c times f prime of x. In other words, when I take the derivative, I multiply the constant by the derivative. So if f of x is equal to a constant multiplied by an exponent, then the derivative is the constant times f prime of x. So let's look at some examples like that. So if I have f of x is equal to 8x cubed, to do the derivative, I still bring the 3 down, but I'm going to take the 3 and multiply it by 8x, decrease your power by 1 is 2. So you're still bringing the 3 down, but you're multiplying it by the function with the exponent decreased by 1. So this really becomes f prime of x is equal to 3 times 8 is 24x squared. Okay, my next one, prime of x. So I'm going to bring the 10 down and multiply it by negative 5, x exponent, decrease that by 1 is 9. So that is f prime of x is 10 times negative 5, negative 50, x exponent 9. Okay, same thing here. We need a power. So instead of having 4 root x, I'm going to say this is 4 times x to the 1/2. Now the exponent of 1/2 only goes to the x because it was just the square root of x. So to take the derivative, I bring the 1/2 down and multiply it by 4x, decrease your power by 1. So 1/2 take away 1 is -1/2. Okay, so 1/2 of 4 is 2 times x to the -1/2. So again, we don't want negative exponents, we want positive exponents. So 2 stays in the numerator, and x to the +1/2 goes to the denominator. But again, I started with roots, not exponents, so I want my answer to end with roots. So my final answer will be 2 over the square root of x. And no, you don't need to rationalize that. That would be your final answer. Okay, so here I want to write it as a power. So instead of 6 over x cubed, I'm going to write it as 6 times x to the -3. So I bring my exponent down to find the derivative. So that's -3 times 6x to the exponent of, decrease it by 1. So -4 decreased by 1 is -3 decreased by 1 is -4. Okay, so 3 times 6 is -18, x exponent -4. Again, I am not allowed to have an answer that has a negative exponent, so -18 stays in the numerator, and x to the +4 is in the denominator, and that would be my final answer. So we've seen questions where we have no coefficient in front and ones where we do have a coefficient in front. Let's just go and do a word problem, because I really want you to remember what it is you're doing when you find a derivative. And what you're doing when you find a derivative is finding the slope of a tangent line to that curve. So we have this point. We want to find at what point on the hyperbola xy equals 12 is the tangent line parallel to the line y equals -3x. So first of all, we need a y equals equation here. So I have xy equals to 12. So to get y by itself, let's divide both sides by x. So I get y equals 12 over x. Now, before I want to find the derivative of that, I'm going to write it using an exponent. So it's going to be 12x to the -1. So now I can find the derivative. So y prime is, bring the -1 down. So -1 times 12x to the, decrease your exponent by 1. So -1 decreased by 1 is -2. So this is going to be -1 times 12 is -12, x to the -2. And again, we want to write that with positive exponents. So -12 stays in the numerator, and x squared comes down to be in the denominator. Now remember, that is the slope. Derivatives are slope. So we want to find at what point on the hyperbola is the tangent parallel to this line here. So what do we know about parallel lines? Lines are parallel if they have the same slope. And in fact, parallel lines have so much in common, it's just a shame they'll never meet. So if this slope is -3, the slope of a tangent line parallel to it will also be -3. So I said that the slope of the tangent line is really the derivative. So I now know that -3 is equal to -12 over x squared. So I just want to solve for x here. So what I'm going to do is multiply both sides by x squared to get rid of my denominator. And then I'll divide both sides by -3 to get x squared by itself. So -12 divided by -3 is 4. So x squared is equal to 4. To solve for x, I'm going to take the square root. So the square root is going to be plus or minus the root of 4, which is plus or minus 2. So I have two possible points of tangency, positive and -2. To find the y value that goes with it, I go back up to my original equation, or my function here, y equals 12 over x. So if x equals +2, then I can say that y equals 12 divided by 2, y equals 6. So one of the points is 2 and 6. Conversely, if x is equal to -2, then I know that y equals 12 over -2, which is -6. So another point is -2 and -6. So those are the 2 points of tangency to the hyperbola that have a slope of -3. Okay, so now that you've applied power rule and you know how to do power rule, maybe you'll appreciate this joke here. So the derivative operator says to x cubed, why are you deriving yourself? The derivative operator says to 3x squared, why are you deriving yourself? The derivative operator says to 6x, why are you deriving yourself? And then the derivative operator says to 6, why are you deriving yourself? Why are you? It's all gone. You guys get that? Now that you know the power rule, derivative of 6 is 0, so it disappears. So I hope that this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I'll see you for the next one.